Okay, today let us discuss the legal question 689, maximum sum of three non-overlapping subarray. The question description is in a given array of positive integers, find three non-overlapping subarrays with maximum sum. Each subarray will be of size k, and we want to maximize the sum of all three multiply k entries. Return the result as a list of indexes representing the starting position. So the point is starting position of each intervals. If there are multiple answers, return the lexicographically smallest one. Okay, here it it gave us an example. It's 12126715. Okay, the answer for this example is 035. Because the first subarray start from 0 and the size is 2, it's 1 2. Okay, and the second subarray start from index 3 and it's 2 6, and the third subarray start from 5, it's 7 5. So in these three subarrays, with the sum of these three subarrays is size is a maximum. So although there's another subarray 2 1 2 1, but the answer should, because the answer is 132, because it 1 is greater than 0, so we should get a lexicographically smaller one. So answer should be this. Okay, let me think about how to solve this problem. Okay, first let us think about the solution about brute force. About brute force for this array. Okay, first we can, in this example, k is 2. It means for each subarray, its size is 2. Okay, first I can take the first two elements, and then for the rest of elements, okay, first I can take the first two, and then I can take for the rest of element, I can take the first two, or I can take these two, or I can take these two, and I I continuously do this process to calculate each subarray and its sum and find the maximum one. So for this example, the next one is I take these two, and again for the rest elements it's 751. So I can take these two, or I can take these two. Okay. So in this brute force, the time complexity is I can have the for the element, I have to continually take k elements. So maybe this two, or this two, or this two, or this two. So, and for each subarray, I need to go through k elements to calculate its sum. So total n elements, and for each element, for each subarray, I need to go through k elements to calculate sum, and I have to total run this loop 3 times. So time complexity is a multiply case 3. So this is a time complexity. So how can we improve this brute force? Let me think about one concept is pre-sum. Okay, in this example, the element index is 0 to 7, and this is our element. So we can use the concept of pre-sum is, okay, we can pre-sum with total n minus 1 element. Okay, so in this means the first element is sum is 1, and the first two elements sum is 3, and the first three elements sum is 4. So in this pre-sum array, pre-sum I means sum of the first I elements. So if we want to know the element from element 2 and element 4, so we can know, we use pre-sum 4. It means the first four elements minus first one element. So it means I get the element sum of the element from element 2 to element 4. So total is 5. Okay, this is the concept of pre-sum. So for this, so use this, we can improve the brute force. So originally, each time I have to go through k elements to calculate sums, but because we can use presum to store this presum information in advance, so we can quickly get from element I to element j what is this sum. So in this situation, we reduce this k. So with Prism, we can improve our brute force to n three times. So this is a good improvement. Okay. Okay. Let me think how to improve it because brute force is performance is not good. Okay. Let me think about this array. We can separate this array. We want to separate this array into three parts: left subarray, middle subarray, and the right subarray. Okay, in the middle subarray, because we have to divide this array into three parts, so it means in the middle subarray, its start index should be only we can only move from this case to. So it means its start index can only start from k, index k to a minus 2k. Again, similarly, for the left. For the left subarray, its index can be start from 0 to this is a minus 3 case. Okay, for the right array again, its start index can be start from the 2k and continue to a minus k. Okay, so we can move the middle subarray. For example, the first middle subarray, we can assume this star index star position is like this. So in these situations, okay, we can check, okay, what is the maximum sum of the left subarray and what is the maximum sum of the right subarray. So now we can get information about these three subarray. Its maxima. So we can continue to go through this. We can continue to move the middle element. So we can know, okay, what is the what is the maximum sum of the left, middle, and the right subarray. So for this, the time complexity is because we have to only move uh, these elements. So time complexity is a minus 2k minus k. So it's a minus 3k. And the space complexity, okay, for each time we have to calculate how many elements we have to calculate k elements in subarray. Again, if we can k elements in this subarray, okay, so time complexity is k. So this is the time complexity. Okay, and we want to reduce this. We want to reduce this. For this, I means okay for each time when next middle subarray start from this. Okay, for the left subarray, we want to know from 0 to 1 what is its maximum length, maximum sum. Again, from for the right, from we want to know for subarray element for index 4 to 7. What is its maximum sum? So although we already use the pre-sum to calculate it, but for each time we still have to move the right subarray to check, okay, is this the which one is the largest? Again, if I move my middle, okay, so each time I have to check which one in the right subarray is larger. So in this kind of situations, if I can calculate it in advance, I means for index for right subarray, if its star index is I, what is its maximum sum star index? Again, for the left subarray I, it means for the if the star index, if the end index, for example, this is middle. Okay, this is middle. Okay, if the end, this is the end index of left subarray. So left I means if the end index it's I, what what is its maximum sum star index. Okay, so it means we have DP. We can use DP to solve this problem because we have to store this information in advance, and so we can quickly solve this question. So in this kind of situation, we for each time when we move the when we move the middle, the range of middle subarray, we can quickly get what is the maximum sum star index of maximum sum in the left subarray, and and what is the maximum index star index, what is the maximum sum, what is the star, what is the maximum sum, what is the star index, what is the star index of maximum sum in subarray, in right subarray. So for this, I can reduce this k. I can reduce this. I don't have to do this. So time complexity is a minus 3k. Okay, let me start to coding to check it. So as our as as a discussion, first we have a pre-sum to store this information in advance so we can quickly get from element I to element j what is sum. Okay, so it's numbers length and int pre-sum is new int minus 1. I is the 1. I is equal I minus I add. So again, pre-sum I it means for the first I elements, okay, its sum is equal to the previous element at numbers I minus 1. Okay, now we have the pre-sum information. Okay, okay, now we have to calculate the information about the left. For the left array, it store the information is the end index. If I end with I, what is its maximum start position of its maximum sum. Okay, so I use the information is left its new int n I is k minus 1. I is okay. For the left, for for this example, I can start with this position because k is 2, so it means the end of the left subarray is k minus 1. It's k minus 1. So I start from k minus 1 and I go to the last element. Okay, and I have index is 0. Okay, I have a pre-sum. It's I have a pre-sum is pre-sum I add 1 minus pre-sum I minus 1 minus k. Okay, I want to know the yes, first two minus yes, this is correct. So if pre-sum is equal to max, I will set left I minus k, and it means we end with I, and its max sum start position is this. Okay, and max is p sum. If A is not equal, I will set left I is left I minus 1. Again, we have another right. New int. Again, max is 0 for int. If we start from a minus k, I minus minus. Okay, again, in p sum is equal to pre sum. For this, it should be for left for the left one. Okay, it should be a minus k pre-sum I. Pre-sum I at k minus pre-sum I. Yes. So if pre-sum is greater equal than max, I will set right I is equal to I. Max is pre-sum. Again else right is equal to right I minus 1. Why this I we have to use equal because the as the problem we need to return the less graphic smallest one. So if the current p sum is greater is equal than right one, we have to use this index. Okay. Now we all have the information. So let us calculate it in 3 Okay, so as we mentioned, middle is from k to n minus 1, n minus 2k. For in I is k n minus 2k. Okay, so the left star index is equal to left I minus 1, and the right star is equal to right. I think so. If this is I, this is I left index is like I minus 1, and for the right it's I minus I at k. Okay, so it means its total, it's Poisson left at the k minus Poisson left. So this is the maximum sum of the left index at Poisson I at k minus Poisson I at Poisson R at k minus Poisson R. So if total is greater than the max, answer 0 then L, answer 1 is I, answer 2 is R, and the total is max total. So return answer. Okay, let me try it. Okay, there are some syntax error. Let me correct it. Minus 2. Okay, this should be right I. Okay, okay, good. Happy coding.